Okay, welcome back. Now we're going to be talking about doing a little self-guided exercise, and I hope that that's going to be enjoyable for you. We're going to try to take the things we've been learning about in the previous couple of modules and put them together to build a model of delta notch patterning. There's a lot of biology here, which we're not going to have time to go into a great deal of detail with today. But there'll be at least, I think, a little bit of an illustration of how powerful these techniques can be when you put them into a multicellular context. As always, I need to remind you that this module is live streamed, recorded, and distributed on YouTube afterwards. And I want to thank our funding sources at NIH and NSF. So I'm going to tell you a little bit about what delta notch patterning is. Both the biological background, then we'll introduce a very, very simplified mathematical model of delta notch by Collier. In reality, delta notch is a fairly complex signaling mechanism, and there are much fancier models of delta notch patterning, especially by Lorenzo Veschini and by Allon, Uri Allon. Those are worth looking at. If you can implement the simple one, though, changing to the more complex ones is not that hard. Actually, the example of the segmentation, the semitogenesis, that simulation has delta notch patterning in it. Then we'll build a very simple delta notch model. I'll talk a little bit about how to iterate over cell neighbors because we didn't really go into that in detail earlier. I'll also show you how to implement a steering panel, which is a very useful feature to have in your simulations. And then we will gradually extend that delta notch model. And depending on how the time goes, we will get through a variety of exercises. If we can do them here, great. If not, you'll be able to explore them on your own at home. And versions of this code are available online. The finished versions of this code are available online. So let's start out again. For the antimony portion of this code, I recommend Herbert's great textbook, Systems Biology Introduction to Pathway Modeling. I recommend the online documentation at the Tellurium website and our Tellurium antimony cheat sheet. I will also remind you of the antimony syntax. The key things are that you need to define your model as a string, a text string inside of triple quotes. That string will follow antimony syntax. Double slash and hash are comment characters. Semicolon is the delimiter, colon names rate laws, and is also used inside of events. The key concept in antimony is chemical reaction, and you typically write rate laws in the form of something is transformed to something else, semicolon, and then the rate. You have to remember that you have to define all parameters in the antimony or it'll throw a syntax error. You can write ODEs directly, X apostrophe is dx by dt, and you can specify dynamic relationships with the colon equals rather than the regular equal sign. You can also define events, as we talked about in the previous section, but we're not going to be using those today. Okay, to also want to remind you about the things that we just discussed, which is that we can load a free-floating antimony model, add free-floating antimony model. We can load antimony models to cells, which is what we're going to be doing today. Add antimony model to cell. A model name specifies the handle for that model from CC3D Python. Step size specifies the conversion from antimony time units to MCS. We can load into individual cells. We can load into cells of a given ID in a list. We can load into all cells of a given type. If we want to read antimony from a file, instead of saying model string equals, we say model file equals. We have to know the path name, though, which isn't always the trivial thing to do. There are some convenience functions inside of Twitter that tell you how to get the path names for things. And there is that integrator Gillespie option. To time step antimony models, we'll use self.timestep. And again, I recommend looking at the Twitter snippets, code snippets. So let's talk a little bit about delta notch patterning. Very often in tissues, you'll see a checkerboard pattern. And it's not quite a checkerboard because checkerboards have equal numbers of light and dark squares. This is a pattern in which you have more like a pattern where you have one dark surrounded by 9 lights. So it's more of a salt and pepper pattern, if you like. This kind of patterning occurs in the human intestinal crypt, at the base of the crypt, colonic crypt. It happens in the hair cells of the Drosophila inner ear. It happens in zebrafish photoreceptors. You have a single cell surrounded by, of one type, surrounded by cells of a different type. That happens with hairs generically as much as also. Otherwise, it happens in color coat pattern and color coordination in fish as well. There are some good reviews on this. As Eric Lai, notch signaling, control of cell communication, cell fate is important. Both dynamic cell state in response to delta notch, cell differentiation, and cell proliferation can all be controlled by delta notch in different situations. We did a little simulation last week of angiogenesis. In reality, all the cells in those simulations had the same properties. In sprouting angiogenesis in embryos and also in adults during wound healing, the endothelial cell at the tip of a sprout has different properties from those in the bulk of the sprout. And that choice between being a leader cell or a follower cell is determined by delta notch patterning. So delta notch is a very critical signaling mechanism during development, wound healing, homeostasis, and also in cancer. Delta notch is what's called a juxtacrine signal. It's a contact signal that's mediated between two cells. In cell adhesion, we have what are called homophilic bonds. A cadherin on one cell wants to bind to the same cadherin on an opposing cell. Apposing, APP, for in contact, not opposing, although it might be that as well. In the case of delta notch, you have two transmembrane proteins, both of which are receptors and both of which are ligands. And it works as follows. Delta on one cell wants to bind to notch on the other cell. So you need delta on one cell and notch on the opposing cell. When they bind, they send signals. Primarily, they're sent through the notch, through what's called notch intracellular domain. So when notch binds to delta, there's a process which actually splits the notch molecule, and the notch intracellular domain, NICD, notch intracellular domain, comes off the membrane and sends a signal. Of course, once it's cleaved, it's not on the membrane to mediate that signal again. And so it's an intrinsically self-limiting signal mechanism. The cell will then synthesize more notch and put it back on the membrane. Cells can have both delta and notch going at the same time. They can have expression of both at the same time. And delta and notch, what's called in trans, that is delta on one cell and notch on another cell, behave differently from delta and notch in cis, where you have delta and notch next to each other on the same cell. In general, delta and notch next to each other on the same cell cancel each other out. It's not universal, but generically, that's more or less what you can think of. And so either delta or notch will win for a given cell. But at least to begin with, you can have delta and notch on the same cell, and two cells that are next to each other will both have delta and both have notch. There is a cross inhibition if you look through this little loop. So notch in a cell, active notch in a cell, inhibits delta in the same cell. And if you'll notice that delta and notch, as we have them drawn here, delta in cell 1 promotes notch in cell 2, which inhibits delta in cell 2. That means that inhibiting delta in cell 2 reduces the notch signal in cell 2, which releases the inhibition of delta, which upregulates delta. And so the more delta we have in the cell, the more notch we get, and the less notch we get, and vice versa. But it's mediated through the other cell. So this is what's called a toggle. If the two cells start out with approximately equal amounts of delta and notch, that's unstable, but can sit around for a long time. If one cell has a high level of notch, it'll tend to force its neighbor to have high delta. If it has a high delta, it'll tend to force its neighbor to have high notch. As we know geometrically, if we've done physics, you can have situations which are called frustrated, in which you can't resolve all of the connections you'd like. On a hexagonal lattice, as drawn here, I can have a high delta cell surrounded by high notch cells, and it's consistent. But if I draw an arbitrary geometry, it may be that if I follow 3 cells in a row, I can't have them always come back in a self-consistent way. And so I can have frustration where a cell would like to be high delta, but it has a lot of high delta cells around it. And so there's a lot of dynamics that can go on, and you actually get oscillations of delta and notch for realistic geometries. Okay. The actual mechanism of what's going on is relatively elaborate. And as I mentioned, there's some beautiful simulations of that, models of that. We're going to use a very, very simple model of Collier from 1996, which really finesses all of that. Instead of considering delta in the cell and delta on the membrane, notch in the cell on the membrane, cleaved notch, and so on, it's going to just assert that there is delta active and notch active in the cells. And we're going to have a single number, D, which is the amount of active delta in our cell, and a single number, N, which is the amount of active notch in the cell. And we're going to say that both of these molecules decay with first-order kinetics. That's dd by dt equals minus nu times d. That's first-order decay, so that the molecule has a lifetime. dn by dt is equal to minus n, first-order decay. And we're going to say that the synthesis of the molecules is regulated by something else. In the case of delta, synthesis of delta is inhibited by the active notch in my cell. This is that Hill function that we looked at earlier. It's the inhibitory Hill function. 1 over 1 plus b times n to the h. Anytime you see an exponent of h, it's a Hill function. So the more notch I have in my cell, the less delta I produce. Okay. The production of notch, on the other hand, is determined by an excitatory Hill function. But there's a difference. delta here is not the delta in my cell, it's the delta in my neighboring cells. Now, in reality, my ability to sense delta depends on how much notch I have. So there should be a multiplication by notch and some other things going on, which is why I say this is quite an oversimplified model. But for our purposes, it's enough, and it will illustrate all of the fascinating patterning that happens in delta and notch. So again, let's walk through this. The production of delta in my current cell is 1 if I have no notch, and is reduced as the amount of notch in my current cell goes up. And that molecule has a lifetime, decays. The amount of notch in my current cell is determined not by the amount of delta I have in my cell, but by the amount of delta in my neighboring cells. And so to run this simulation, we will have to couple our model of what's going on inside the cell to what's going on in our neighbors. That's why it's critically something you can do in something like CompuCell that's hard to do in a non-spatial model. And then we say that notch decays at some time constant. And there's some parameter values here. The equilibrium threshold of notch is quite small. That capital K that we normally would write here as lowercase a is 0.01. And the gain, the inhibition of notch, of delta by notch in that first equation has a factor of 100, makes it quite big. And the Hill exponent is 2, which is pretty weak. Okay, any questions about that basic model so far? When we run this on a square lattice, and here the square lattice will disappear, we start out with things a little bit random. They fight each other, and you'll see blue, high delta, surrounded by low delta cells, and you'll see some cells don't know what to do because they have some neighbors that are high delta and some that are low. And eventually, in this particular case, the pattern equilibrates to something where all of the cells have found the state that they want. But depending on the geometry, that may or may not be possible. So that's the simulation that we want to run. What you're going to do is you're first going to use uniform initializer to create a lattice with cells. You're going to put this model in antimony. You're going to add it to each cell independently. Then at each time step, you're going to loop over all the cells. For each cell, you're going to look at its neighbors. You're going to read the delta value on the neighboring cells to calculate that D average. You'll set a new value of delta average from the outside into my model. You'll iterate over you'll time step the internal model of the network, and then you'll visualize it. There's a question in a square lattice, are there 4 neighbors or 6 neighbors surrounding the cell? Well, if I freeze the lattice, then you can actually define the neighbor range that you want to look at. So the answer is that that's up to you to decide. But in general, one of the things that you might want to do, and we won't do that initially, is you might want to weight the contribution of the neighbor by the contact area. So you might say that if 2 cells are contacting each other over a big area, that has a big effect. But if they're only touching at the corner, then it's a small effect. And we'll find that when you iterate over neighbors, it tells you not only am I touching another cell, but it'll tell me how much area I have in contact. And so if I wanted to build a slightly fancier model, I would weight the delta from each cell by the contact area with that cell. So it's a great question. Okay, so I'd like people now to go through this in steps. Again, it's a guided exercise. I'd like you to try to do this. If people have trouble doing it, then I can come back and help out. The exercise will be first create and I have a special number because I want there to be an equal, a uniform number of cells. So create a 42 by 42 by 1 simulation domain. Use Wizard to do this. Choose volume local flex and contact constraint. Fill the domain with cells of width 7, so that'll come out even. In the steppables, assign a target volume of 50, lambda volume of 2, with periodic boundary conditions. Okay, so that's the first thing you want to do. Then you'll write an antimony string corresponding to the ODE equations. And we'll write it as ODE things. We're not going to write it as rates for the moment. Then you'll load the antimony model into all cells. You shall initialize the values of delta and notch on each cell to be random numbers between 0.9 and 1. You'll calculate the average value of delta over the neighbors of each cell, pass it to the original cell, and then you'll calculate, create auxiliary fields to display delta and notch for each cell. Okay. So why don't people do this in steps? I'll let you work on it, and then we can do it together. So the first step is simply to use Wizard to create a simulation domain. So why don't people take a minute or two to try to do this? You create a 42 by 42 by 1 simulation with periodic boundary conditions, volume local flex and contact constraint, and then use uniform initializer for cell size 7. And then in the start function, give every cell a target volume of 50, lambda volume of 2. All right. I think that should be something that people, if you don't remember how to do it from last week, dust off your, it's all in Wizard, pretty much all in Wizard. So why don't people try doing that? I'll give people a few minutes. Is that part of the assignment clear? Are there any questions about that for the moment? So I'll do it with you while people are working on it. I've launched Wizard, told it to create a new simulation. I'll put it in that demo folder. Maybe not the best idea, but it's there. And I'll just call it delta notch, maybe in class, so we know that it's that one. I'll say I want Python and XML. I said to make the lattice 42 by 42 with periodic boundary conditions. And I'm using a uniform initializer. And I'm only going to have one kind of cell, so I guess I can call it cell for the moment. I don't have any chemical fields, so I skipped that. And I said volume local flex, contact energy, you're going to need cell neighbors, but that's turned on by default, so you're okay with that. We're not having cells grow or divide at the moment, so we don't need those. So that's it. And now I've said we're going to, in the steppable file, assign a target volume of 50, lambda volume of 2. So let's go to the steppables. In my start function, I'm going to iterate over all cells. CC3D Python, visit all cells. And if I don't remember the commands for target volume, cell attribute, lambda volume, cell attribute, cell attribute, target volume, and I'm going to be setting lambda volume and target volume. And I said make lambda volume 2. And I said make target volume 50. And then the other thing I'm going to have to do is in my XML, I'm going to have to go down to where I have uniform initializer. And I want to do the whole lattice. So I'll have to set the bottom corner to 0. The top corner, I think I said was 42. So I need to go to 42. Actually, I probably need to go to 43 for that. And the width is already set to 7. So this isn't going to do much, but let's see whether it works. There. Crashed on. Test output directory. Well, that's a new one for me. I haven't seen that error before. Did I write something where I don't want to be doing it? I'm going to set the debug output frequency to 0. See whether that helps. Did anybody else have it work or not work? Okay. So it did create the initial picture, but it says name L cell is not defined, which means I made a typo in my simulation. It's in my Python probably. I accidentally put an L there. Okay. Thank you. Okay, well, you guys are much more on top of things than I am here. Everybody's okay now. So now we've got our initial picture. The next step, okay, so the next thing to do is to type the delta notch model in. And we need the basic antimony syntax, which is J1 colon nothing goes to X, implements dx by dt equals something. And remember that the caret is the exponentiation operator in antimony, and that we have to give our parameter values. You're just defining a model string. And my recommendation to everybody was you put the model string up at the top after the import statements and before the class definitions in the Python. And I'll do this silently, but please do it yourself. Don't wait for me. You may be able to do this more elegantly. And so I really don't recommend following me because I think you probably can come up with a better way of typing it than I am. Sharon asked, don't we have to insert a steppable class? You've already got a steppable created when we ran the wizard. So you don't need to add anything. No, you don't need to define an SPML steppable. That was just a convenience. There is no custom SPML steppable. Giuliano, when he created that simulation that we were running as a demo earlier today, named it SPML steppable just so that you would know what it was about. But the name of the steppable is up to you. Mitosis steppable base, what you inherit from is special. But the name of a steppable is just a handle. You can call a steppable anything you like. Great question. I'm seeing quite a few typos in these slides. I hope people will point those out to me afterwards. I think the one thing that might be a little bit tricky here is that D average that's being passed in has to be put in here as a dummy placeholder. So you have to create a variable or a parameter that's going to carry that value, even though it's not updated by the rate loss. So basically, within the model, the average is a parameter. You don't want to try to write the bar as a symbol. So just create. Yes, the average will be treated as a constant for the moment. We're going to evaluate the average in CompuCell and pass it back to our model. But that's a very good question. That'll be 2 steps down our exercise. And I'll version this, so I'll call that step 2. Actually, all the steps are written out. You have actually versions of this code with all of these steps added one at a time if you get stuck in the demos folder. How are people doing? Do people have this working, or you can't really tell if it works or not because we're not using it. All we're doing is creating a string. The key thing here is to remember the antimony syntax for typing. And I can put this code in the chat if needed. Although I'm not sure I would recommend using my code. You might do better on your own. The next step, well, here's how I did it before. I set the initial values of D and N to something slightly different. Everything else looks about the same. The next thing we have to do is load that antimony string, and we want to do it into all cells. So see if you can figure out in your start function how to load that model that you've just defined into all of your cells. And remember to use the twidit function, add antimony model to cells. Here I've said you could do it by type if you like, but you can load it to all cells too. You don't need the initial conditions. You don't need the integrator. You're not loading it from model files, so those have to be deleted when you paste it in. You can do it inside the loop and add it to an individual cell, or I can do it outside the loop and add it to all cells. Save myself some typing by doing it outside. And I'm afraid, as I say, you really should do it on your own, because following me typing, it's going to be a little hard on the screen. But here I've add antimony model to cell types. I'm not using a model file, so I get rid of that. I have to remember what my model string name was. I called it delta notch model. Now I'm going to have to make this visible. I'm going to actually have to see just a little bit. I see. So I'm going to have to see, there's probably configuration in my twidit that's a little bit funny here, because it looks like I'm actually truncating my line here. I have to remember what I called my cell type. I called my cell type just cell, so that's easy. There we go. Was I editing the wrong file here? I was. I was editing the wrong file. Really messed up, didn't I? Try that again. As I say, you probably do it faster than I would. I'm going to add model to, Antimony model to cell types. There we go. I'm going to read it. Oh, I don't have my model string then. Well, somebody else will have to help me out. Yes. Don't forget to copy my model string. Thank you. You see, you're helping me debug. It'd be better if you see if you're all done, then I can go on. I don't have to do this. Let's see, delta notch model. There's no model file. And I need to call my cell types the cell. And I have to get rid of the other cell types that are there by default. Okay. And I need to give my model name a model name. And instead of calling it model, which I think is confusing, let's call it about DL for delta, or DLN, maybe it's better. Step size, we're going to set I think I gave you a value for step size, didn't I? 0.2. And I said, get rid of initial conditions and integrator. Oh, I see. It got the. Thank you. Is that right now? Okay, we've added our antimony model. And now we need to initialize the antimony model. And when we do this, we're going to have to reference a D and N. And we're going to use the random numbers in NumPy. And you'll notice that NumPy is now automatically loaded. Line 2, import NumPy as NP. And so you're going to have to look up the syntax for getting a random number, if you like. Here it is, though. The random uniform syntax is random uniform min value max value. And so what I'm going to do is I can come down here. And now I have that model loaded. I have to remember what I called it. In my case, I called it DLN. And I'll say cell dot SBML dot DLN is what I called the model. Square bracket, because it's a dictionary entry. And I left my name of my variable D. And I'll say that that's equal to np dot random dot uniform, and then 0.9 to 1.0. Okay. And I have to do the same thing for n. If people are familiar with using NumPy and random numbers, that's great. If you're not, those are things you have to look up usually. NumPy has lots and lots and lots of functions, and that's a case where I wind up Googling the NumPy the NumPy manuals and looking it up. Okay, take a look at that. If you called your model something else, you have to use the handle that you used. If you called your variable something else, use the variable. Yes, thank you. That's a good reason to use the Python code snippets rather than typing it by hand. So I can put the code that I wrote in the chat. Again, the code that I wrote may or may not be the code that you need, because you may have named things differently or you may have done things differently. The important thing is to be following the concepts here. It's always a good idea to try running it, making sure that we didn't create a typo of some kind. Looks like it runs. It doesn't do anything, but it runs. So this is what I did here. And now we have to time step the simulation. Now we're going to time step the simulation in the step function. We can get rid of all this junk in the step function, which is just sitting there to have something in the step function. And we need to call that time stepper, and we'll do that by going to SPML solver, and then it's all the way, maybe it should be the very first thing, time step SPML model. That's all we need to do there. And again, I recommend always checking that your simulation doesn't crash after you've made a change. I also am a big believer in versioning things. So if you're going to save things, save them as version 1, version 2, version 3. Okay, everybody got that put in? That one's pretty straightforward, I think. Now, the next thing is the one thing that we have to do that's a little bit more elaborate. And that is we have to loop over each cell. For each cell, we find its neighbors. We read their delta values. We average those delta values, and we pass it back. Now, in our particular case, there is no medium. Everything is full of cells. But in principle, we might have a simulation in which we have cells that don't have delta or notch on them, or cells that have medium. And so when we do our iterator, we want to make sure that we exclude cells that are not of type cell. And so you want to put in a little check if neighbor, which checks that the cells are actually real cells. Okay. And let me just explain how to do that, because we haven't really talked about neighbor iterators yet. We already have the neighbor tracker plugin implemented by default. It's a little odd that you have to turn it on, but in the principle, you don't get anything for free. If you don't want to know what your neighbors are, you have to say you want that. But that's so common, it's turned on automatically. There is a function in CompuCell called self.getNeighborDataList, which is applied to cells. And the one thing that we have to be aware of is that it returns not just the list of neighbors, but the list of neighbors and the contact area between us and our cell and the neighboring cells. And that's actually pretty convenient, because very often you want to weight things by the amount of contact. If you have a lot of contact, the signal is more important than if you have a little bit. And what we'll do is we'll set some average contact area to average contact to 0, number of neighbors to 0. We'll iterate over the neighbors of the cell. We'll add up here. Here I'm just showing an example for the surface area. Here I'm adding up the common surface area, counting the number of neighbors, and printing the average contact area. That's going to be pretty boring, because in fact all it'll do is return the contact area of everything except medium. In our case, we want to do this now for the delta, and here I'm actually jumping ahead a little bit since we're running out of time, and I'd like to get everybody to get this to work. But is the principle of operation here clear? In the step function, we're going to iterate over all our cells. For each cell, we're going to reset a counter, which is the amount of D of our neighbors and how many neighbors we had. We're going to, for each cell, iterate over our neighbors. It's going to return the pointer to the neighboring cell. If we were going to be smart, we'd weight our result by the contact area, but for today, we're going to ignore that. We're going to sum the D value in the neighboring cell, and then we're going to update the value in our cell from the neighbors, that D average value. Does that make sense? Any questions about that? So let's do that. I'll do that here with my code. I'm going to do this in the step function. So what am I going to do? CC3D Python, visit all cells. Okay, first I'm going to visit all cells. And now I'm going to go back CC3D Python visit, and I'm going to ask for cell neighbors. And it'll automatically paste in return neighbor common surface area. And it even helpfully returns if neighbor for me, because it knows that the medium is a funny thing. And so then here inside the if neighbor, I put in the fact that I'm going to read my D average. The first thing I have to do is reset my D average. So let me do that. D av is equal to 0. And the number of neighbors is equal to 0. And yes, actually, I probably still have got it wrong, don't I? And so, yeah, Dave have to put the G back. Thank you. People told me to fix it, but you didn't tell me that I'd failed to fix it. Of course, I could just use the value that I had there, the name I had there. Okay. And now, what do I have to do? If neighbor, I'm going to say D average plus equals the value in the neighbor. So it would be neighbor dot SBML dot, what did I call it? DLN square bracket D. And then I'll increment my count. Again, in this case, it doesn't matter because I know that everybody's touching everybody else. But if I start out with a single cell by itself in medium, I might not have any neighbors. And so I need to be prepared for that. Okay. And then when I come out of my loop, I need another if, because if I didn't have any neighbors, I don't want to do anything. So if NN, if I have some neighbors, it's a good idea to use these indent bars. If I have some neighbors, then I want to set cell.sbml dot DLN of now D average is equal to DAVG. Okay, does that work for people? If I've got a typo in my code, please point it out. See if it works. Doesn't crash, so I guess I don't have any terrible typos in it. Oh, I know what happened. I didn't. I changed my file name, so I didn't load the new one. So I better double check that. Actually, I may have a typo there that I wasn't aware of. That's the one problem with versioning. Okay, when you put in type, what did you put in? Somebody says they have an error when you iterate by type. When you put your type in, it is to be a list. Okay, so not finding neighbor tracking plugin means that you have to go into your CC3D ML and add the neighbor tracker plugin. That should have been automatically enabled when you did Wizard. But we can add that. That's probably, again, because you're using an old version of CompuCell. But I'll give you that code in a second, Venceslas. Cell list by type is in the, when you're loading your SBML model. In that line is where you have your syntax error, Melanie. So it's where you loaded the SBML model that's causing the problem. Let me get the code for Venceslas. In your XML, Venceslas, you need to add this code. Okay. That will be in the snippets, the code snippets, so you don't have to retype. Melanie, how are you doing in finding your bug? The place that your bug is here when you're loading the Antimony model. And I said to load that by cell type. And remember, the cell type has to be in square brackets. And you probably left out the square brackets because it's a list of cell types. In some ways, it would be nice if it were a single cell type, but you might want to load it into 3 cell types at once, so it expects the list. Great. Anybody else? Any other issues with that? How's it going? So now, although we can't see it, we actually have a delta notch model. Let's make sure it runs for me. It runs. So the last thing that we have to do is we have to display delta and notch. And we do that by creating a tracking field. And the one thing that's a little bit inconvenient about tracking fields is they expect a dictionary entry, but they expect a dictionary entry in cell.dict. They don't expect the dictionary entry in cell.sbml.dict. And so we have to copy the values of D and N from cell.sbml.dict, or in this case, cell.sbml.dln, to cell.dict. Is that clear? So let's do that together. The first thing we have to do is we have to remember where tracking fields go. Tracking fields go after we load steppable base. And if we want a tracking field, CC3D Python, extra fields, automatic tracking, track scalar attribute. And we'll call the, let's see, this is, I'll have to make this a little bit bigger so you could see. We'll call the field name here delta, and the attribute name will be D. And we'll create one for notch. Field name notch, and the attribute name is N. Okay. And then the last thing we have to do to finish the simulation is did I do it again? I pasted my what did I do here? I must keep pasting things into the wrong file, huh? Where are my, oh, let me close that because it's distracting me. Added Antimony Model. What happened to my little iterator to iterate over my cells? I think when I copied it into your into the chat, I accidentally cut it rather than copying it. Okay, so now I have that. Sorry, that should have been the start function. Eventually, I'll get there. That belongs in the start function. And now I need my code for iterating over the step. I seem to have two. I see what happened. Huh. That seems to actually be a bug in Twitter. When I rename things, something funny is happening. So let's see if this is going to work. So I have the initialization, I have the step here. And I apologize to people if this is taking more time than it should. And now I need to put in my tracking fields. Yes, I think that's right. I hit, instead of saving the project, I just saved the I saved the subfile, which was my mistake. Are other people getting it to work correctly? Because boy, I'm not doing so well here. It's a good reason to not copy what I do. And then the last thing I have to do is I have to copy those values from delta into a new dictionary entry. So when I iterate over my cells, I can say cell.dict. I call the D equals that. And the same for him. Does that work for people? Let's see if that works. I hope you're doing better than I am for this. It says couldn't find SBML solver. So that means that I didn't load it properly. Oh, because I called it DLN here. Add Antimony Model, DLN. Time step SBML. I think I probably managed to clobber my, when I saved it wrong, I probably clobbered my results. Anybody get it working? Oh, it's when I did the uniform random. That's where it is. No, DLN here is correct. Did I load it as the DLN, 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 DLN. Okay, so somebody says they've got it working. Who has it working? Somebody says it shows the right pattern. Somebody says it runs. Seems to work. Yes, in the graphics window, choose delta or notch. So I should probably do what I recommend for you to do, which is I'm going to open my simulation here. And I'll open delta notch. I'll run that. So this is the one that I have. This is like Julia Child, where you have it predefined in case there's a problem. And now under cell field, unfortunately, it opens it on the wrong window. So you're not getting it screen shared, but I can open notch here. And let me create another window, new graphics window. And I'll make this one delta. And I'm going to let it run. Okay, does anybody besides me need help with this? Somebody debugged it for me. I appreciate that. Okay. Anybody else need help? Yeah, that's what I did. I typed it wrong. I didn't correct it properly. I said to version things, and then I outsmarted myself with my versioning. All right. If anybody else needs help, let me know. But I think your classmates and compatriots are probably going to be better help than I am. All right, so there were our tracking fields. That was our change. We run it, and you get something like that. Okay, we're out of time for today. I will cover steering panels another day. I have a yellow stripe here because I have a conflict between the cells. The cells on one side are telling it to go in one direction. The cells on the other are telling it to go the other. And so those cells aren't able to make up their mind. If I look at delta, on delta side, they're okay. Let's see if I do a tile. You see the delta cells. You see I've got blue next to blue. This is called frustration. The pattern is not able to resolve itself completely. A perfect checkerboard, every dark cell is next to 4 light cells, and every light cell is next to 4 dark cells. In this case, the high delta cells want to be completely surrounded by low delta cells, but that's not possible because of the number of cells in the simulation. You say your cells are all the same color? In other words, they're all blue or all red? And you're looking at the delta here. So one thing that you can do is you can go to Tools, Configuration. Let's see if it's going to crash on us. Go to Field, and make sure that both delta and notch have the values unset. Instead of saying, don't say fixed, say float here. And make sure that those are both unfixed so that you can see the full range of values. Let me try running that again and see what happens. So this is my basic cell field. I'm going to look at notch here. Hit run. So this time it looks like the pattern is regular. And this is a bug in Player. You'll notice that now it only advances if I click on it. So I'm going to close that graphic window. I'm going to create a new graphic window. Set it to notch. And now I'll hit run and it updates. Well, it's SBML, not SMBL. So that's one thing. Perhaps there's a typo. And is the image updating or is it frozen? Because there is this glitch that sometimes the image updating stops for Edgar. So there are a couple of possibilities if it's not updating. One possibility if it's not updating is that the initial values weren't randomized. So you didn't iterate over all the cells and randomize them. In that case, you won't get this to happen. Another one is that when you're doing your averaging, you're not passing that neighbor average back properly. So those are both possible. Any other questions or comments? Okay. There's quite a bit we can do going forward. There's quite a bit we can go do going forward with this. And as I say, I would like to do that, the remaining sub-exercises here, starting from where we are. I hope people will be able to take the simulation that we have, do a little bit of polishing and debugging on it. If people are having an issue, please do load the code that's in the demos folder and start with that. You can compare the code that you have with the code that you wrote to see if you can find bugs. And I realize we've covered a lot in a day. And as you see, I'm quite capable of making typos myself. So it's not that it's something that happens, that perfect code happens automatically. I'm going to run the module experience questionnaire for the people who've stuck it out. I appreciate the people who did stick it out. I know it was a long day. Please let us know how things went. And we're happy to stick around and talk a little bit more about your questions and comments going forward. So that's a great question. The answer to Lampros's question was, can we embed the program and call it in from someplace else? The answer is yes. I'm not going to be showing that, but TJ later in the week will show you how to do that. CompuCell can be invoked from a command line. So you can use Slurm, for example, to start a CompuCell job. And it also can be coded as pure Python and then called. So for example, if you were using a NumPy optimizer, you can have NumPy call CompuCell. It'll take it a while, but it can return a value to an optimizer. So yes, CompuCell can be in fact called from Python. Jim talks about pscan will auto sweep over parameters. So yes, we'll show you how to do that later in the week. So Venceslas says CellG object has no attribute SMBL. It is SBML. So make sure that you've typed that correctly. Why don't you try? I would suggest try loading the code that we provided in the demos and look at the code next to each other and see whether that you can find the mistake. But my guess is it's a typo.
You can also, if you do just want to look at the code, you can just open the Python files in a text editor as well. You don't have to go through the process of loading it all the way through CompuCell. If you just want to take a quick peek.
Okay, I had the same typo. I wrote SMBL the first time. People caught it for me.